Est-ce que déjà sur le principe de réduire le temps de midi, ça vous va?
Oui.
Ok, on se dit combien de temps avant?
Un quart d'heure.
Un quart d'heure. Une demi-heure avant?
Ouais.
13h30.
Question, on en fait trois, après quel temps? On en fait 4 avant la pause, c'est ça?
Pardon?
On fait 4 avant la pause.
4 bah, si, ça dépend du nombre de questions que vous posez.
J'ai compris.
Donc 13h30, vraiment arriver à l'heure, comme ça on peut avancer vite et on pourra prendre le temps de la pause. Pardon? Bah, soyez là à 25 pour qu'on commence à 13h30. Ah oui, oui.
Après le vendredi,
Bon.
Ah ouais, d'accord. Ah, je vais tomber là. Natacha. Tu es encore plus.
Okay, so okay, so we switch back in English and the floor is yours. The floor is yours.
Hello. So, good morning, everyone. Imagine being fully conscious, intelligent, and aware of everything around you, but you are unable to move or speak. Well, that's the reality for millions of people around the world living with, for example, paralysis. So today, we are going to discuss about one of the most heartbreaking advances in brain-computer interfaces, especially Neuralink and similar technology that are completely decoding and interacting between action and sound. Let's start with the problem. As I said, millions of people, millions of patients, and new cases every year. These people are unable to communicate. Today, the best we can achieve, the best we can do, is eyes tracking interfaces. And honestly, that's quite exhausting. That's quite exhausting, and that's kind of limited because you achieve 5 to 10 words per minute. And imagine trying to have a conversation at that speed, it's almost impossible. Now that's where it gets more exciting. With Neuralink, one surgery, few months of training, and you can achieve a speed of 40 words per minute. That's not improvement, that's transformative. So you're giving voices back to the voiceless. How does it work? We need to understand the brain-speech architecture. So first, when you speak, you activate 3 systems. You have the first one, motor cortex M1, which makes you able to move the lips, move the tongue, move the jaw. You have the second one, the Broca's area, that structure the grammar, the meaning of what you're saying, and the last one, that's the sensory cortex, the one that makes you able to understand what you are saying. Even when patients are completely paralyzed, you still activate motor cortex M1 when you think of a speech. That's where the signal is, and well, that's clean. The brain use 4 layers with speech. The first one is the raw phonemes. That's A, B, C, D, for example. The second one is the motor command, that the specific mouth, lips, and tongue position that are highly organized and measurable. The third one is the semantics meaning, and the last one, the grammatical structure, to organize your sentences. With Neuralink, we focus on the second layer, the motor command, because that's where the signal is the strongest, it's measurable and repeatable. That's where the goal is. Nevertheless, we face challenges because the signal is quite tiny, around 100 microvolt. It's like trying to hear a whisper in a thunderstorm. So when you think of a speech, something happens. beta boomer spikes on the cortex electrode. The range is around 12 to 30 hertz, and that's the beta band. So when you imagine of a speech, the whisper becomes clear, and you can now decode it. So you have three approaches to record EEG, non-invasive. It's electrode on the scalp, no surgery required. Accuracy is quite low. So there is a second one, ECOG, semi-invasive, electrode under skull, brain surfer, little surgery, good signal quality. And the last one, microelectrodes. It's fully invasive, Neuralink approach inside brain tissue. The signal is perfect and your accuracy is better.
Okay, so now I'm gonna explain to you guys how Neuralink can transform brain signal to readable text. So first of all, they capture a signal from the motor cortex, but it's a very weak signal. It's about 100 microvolts. So they use a low amplifier. You can gain about 10,000 times 10,000, and they put some filter, analog and digital filter to remove the noise. After that, they try to extract some features. There is like 1,000 electrodes, and you have to compress all of this data with a spectral analysis to get about 10 variable. And you after that you put it on a decoder. It's a machine learning decoder. I'm going to talk about it just after, but the fact is it's going to search some pattern in the data to get some text, and at the end you're gonna transform it into a text. So machine learning, first of all, they tried it with a linear baseline. But the main problem was the memory, because you just get the answer without what you said before. But you know that you need to say what you want. You have to know what you say, obviously. After that, they tried with classic ML, but they only recognize a basic pattern. That's why they use deep learning with neuronal aspects. It means that they use a deep learning model based on brain, so with neurons, and that's how they get some probability about what's going to be the next letter or word, which is a good example. If we get the letter H and E, after that there is more probability that the next letter is going to be L than Z. Now we're going to talk about the engineering part, the hardware engineering part. So the chip is about the size of a coin, basically, and this is encapsulated in a biocomposite compatible with human. It's mainly in titanium, and the threads are what? The thread are in a polymer. Sorry, in a polymer, and the contacts are in gold or platinum. That's because it's conductive, and it's very important to have flexibility, because if it's rigid, you're going to have some inflammation or immune response, and it's very bad. That's why the main problem is the flexibility in the brain, because the brain is soft and it's moving. So now we're going to talk about Neuralink in his sector. There is other big projects, and like a BrainGate and a huge company like BlackRock Neurotech. The main advantage of these two Of these two companies are the history, because they have been in this industry for a long time. But Neuralink, the advantage is they can provide the whole thing. It means the hardware, the surgery, and the AI, and that's why they are very competitive in their sector. And finally, this is the different phase on the different process. First, they tested on the rodent to see the biocompatibility. After that, they went to primates because of the anatomy, and their brain tissue are pretty close to human tissue. And in 2023, the regulatory give them the possibility to test on human, and they try it on human in 2024. But it was not concluent.
So let's went from this theory to the reality here. We're going to speak about like T5. T5 is the human test subject they want to test this onto. This guy was like quadriplegic after diving accident, and the thing is, he was like paralyzed from his neck, below his neck, like everything was paralyzed. And the thing is, he has like it's not still like he could like think like everybody else, but just doesn't express it. And the thing is, in January 2024, they got like they do surgery. It took like only 1 hour, and then like 0 complications on it. And the thing is, like a few weeks after, like a bit like 3 weeks after it, he could like I won't say speak, but he could like do some words, like 10-15 words per minute. So it's like better than nothing, I guess. And even him like said like it works, it actually works. So I think it's pretty solid from this point of view. So from this emotion, let's look the odd data. So here is like the data after like 9 months. So you can see he went from like 10 words per minute just after the operation. That's like 40 words per minute. Just to get like a bit of context here, if you have like eye tracking, like like technology, it's like 5 to 10 words per minute. So here, like 40 words per minute is like 4 times what you can do with the eye tracking technology. And the thing is, there's like a barrier if you want to like have like a fluent speech. It's like about like 30 words per minute. The normal human speaks like 150 words per minute. But the thing is, if you have like a slow conversation, like 30 works. So like 40, like pretty good. And you can also like do like 3D games too. That's what it does. And the thing is, it helps like those people to be not as isolated as they have. So that's pretty good. So how do we achieve like this speed? The thing is, here is like the optimized pipeline. So as like Francois just told before, they just capture the signals, they just filter the noise, everything. Then they put it like into the ML decoder. So they just like take the signals and make phonemes. And when they get phonemes, they can make words. And the thing is, everything like makes into like 100 milliseconds. So that's very quick. And the thing is, if you went to like 200 milliseconds, 300 milliseconds, the problem is the fluency of the speech. And so you just speaks like this person who's just not the same stuff. And how about like the future of this? So 25, 27, they want to do like, as François said, to like the FDA approval. So the thing is, FDA approval is like helps every regulation to go quicker, to every like paper they need to do quicker. So that helps being commercialized, and also to have like more patients. I think actually they have like 9 patients, if I'm not mistaken. And so the T5 patients called Northern, and they have like a few more now, which are working like better and better. So that's better. And the 2028 and like 2032, they probably want to like. The thing is, the implant is like 100K, so they want to like divide the price in half, which is like 50K, and also to integrate like AI into the product. But the thing is, the most interesting stuff is like in the 2033 plus timeline. Actually, it's like a one-way in. So they take information from your brain and they just put it into the ML decoder and just say the word. So it's like one sense. If you want to do like a switch, so like the other sense, it's like way harder to get some feeling. For instance, like if you touch something and you want to have like the impression of the honor of the table of everything, you need to have information back, and that's not actually the case. So probably want to in a few years. Thanks.
So any questions in the audience? One question. Is it working the URL, the email?
Yes.
You're gonna try.
So I've got two questions, quick questions. During that time, you can install the next one. So what is BCI? You mentioned on your slide.
Yeah.
BCI.
Yeah, basically, it's for the FDA regulations to the thing is to be commercialized. It's the way to be commercialized.
BCI means
I don't know the meaning of it. I just know what.
BCI,
Yes, yeah.
which means
Brain computer interface.
cool. And can you show us again the structure of the brain?
Oh, yeah.
It is called the Broca area, right? You know where it comes from? Broca?
The name of it?
Yeah.
I don't know. Do you know it?
No.
Just like.
Il y a un hôpital Broca à Paris? Si, il y a un hôpital Broca.
Peut-être.
C'est un indice. Ok. Ah ouais, c'est bon. C'est un médecin français.
Ah, ok, d'accord.
Broca, l'hôpital Broca. Broca, grand chirurgien français.
Ok.
Et la question subsidiaire, c'était pendant que vous en allez, laissez-lui la place, laissez-le s'installer. Pourquoi on était bon en chirurgie du cerveau en France? Pourquoi est-ce qu'on est bon en chirurgie en France, et en particulier sur le cerveau? On a trouvé les os du cerveau qui étaient à quoi ils servaient. On n'a pas eu. Pourquoi est-ce qu'on est bon à ce genre de truc? Pourquoi est-ce qu'on est bon en chirurgie en France? Oh.
La formation.
Dans les années 1900, on était très bon en France en chirurgie. 1900 en chirurgie, on a trouvé les os du cerveau, comment on a fait ça? À quoi elles servent? Pas une idée.
Avec des électrodes.
On n'a pas mis vite, je voulais poser la question tant que vous étiez un peu dehors. Ça va me faire peur. On était bon en France en chirurgie parce qu'on a eu des guerres napoléoniennes, et on a eu 14-18, on a eu 39-45. On a eu des gars où on a vu des balles qui sont rentrées dans la tête, qui sont ressorties, et on a détruit une partie du cerveau, et on a vu la zone qui ne marchait plus. Le mec, il ne marchait plus, il y avait des gens qui ne marchaient plus. Le mec, il ne parlait plus. Donc en fait, en ayant plein de balles qui sont passées dans tous les sens, eh ben, on s'est dit, ah bah alors, ce bout-là, il sert à ça. Ah, donc, voilà. C'est pour ça que vous avez plein de médecins français qui ont des noms de cerveau et de je sais pas quoi. Voilà, madame, tu peux rentrer maintenant. C'était des blagues de chirurgiens, c'était pas très bien. C'est pour ça qu'il y a beaucoup de noms français dans l'anatomie. Okay, next.
So today, me and my partner Leo are going to present you photonic chips applied to artificial intelligence. So first, we are going to present you what are photonic chips and their context of application. Secondly, we are going to present the components and the functioning of photonic chips, following by the AA revolution with those chips. And then we are going to present real-world applications and industry examples to be more clear. And followed by the future outlooks, what is the potential growth of photonic chips on the market, which eventually should convince you to invest in this technology. So what are photonic integrated circuits? Those are devices that integrate multiple optical components, such as lasers, waveguides, optical modulators, onto a single chip. And the main difference with classic microelectronics is that photonic chips integrate and use photons like particles instead of electrons to carry, process, and transmit information. So I'm going to develop further their characteristics, but globally they have a higher bandwidth than classic microelectronics, as light can carry a huge amount of data simultaneously. And they also have a lower latency and higher speed as light travels faster. And they also have a better energy efficiency. They do not overheat as it is the case in microelectronics, and they can be, of course, miniaturized. Photonic chips applied to artificial intelligence can have impacts on 4 major sectors. In telecommunications for optical fiber communication networks. I was also thinking about sensors for LiDAR and autonomous vehicles. They use AI and a lot of parameters. For data centers, of course, because they need high-speed interconnection between their servers. And last but not least, for quantum computing, as it needs a lot of computing power. So, in what context did photonic chip appear? So, as you know, AI has driven an exponential need for computational power. We are using larger and larger AI models. We went from millions to hundreds of billions of parameters, and we need a massive computation power. But the problem is that while the demand for AI is growing exponentially, the efficiency in microelectronics does not follow. As you can see with this graph made by Bain and Company in 2025, we can see that over time there is a gap between the compute demand in AI model and the efficiency in electronic chip. And the more we are moving in time, the wider is the gap. So this is a major issue today. And as we study in this course, we are suffering from the effect of, electronic chips have fundamental limits. We are in the slow of Moore's law, because we cannot reduce indefinitely the size of the transistor's channel without suffering from quantum effects, Thunder's effect, from silicon atoms, and we cannot increase the clock frequencies of the chips without overheating. So photonic chips can be a solution because they do not behave like charged particles. They have no resistance heating, and they do not heat the materials as electrons do, and they have a higher speed. So in this picture, you can see the major components of photonic chip. I tried to make it simple, but globally you have a laser that injects light into the chips, and this light is guided by waveguide, optical waveguides. They show the path to the light, and the optical modulator encodes information onto the light by changing its intensity or its phase. And the couplers, they split or combine the light paths, which enable parallel signal propagation. And the photodiode is used to convert this signal into electricity. So the major difference is that microelectronic chips operate almost exclusively with binary computation, which is quite low compared to photonic chips, because the calculations, such as multiplications or sums, are performed by optical interference. and the linear operations are made with the intensity or the phase of the light, and they don't go through binary logic gates. However, we still have remaining challenges for photonic chips today because the components remain larger than transistors, so they took space. The memory materials can wear down with repeated use, and the main issue is that our entire digital world, the servers, the software infrastructure, was built for electrons, and so we need converters to use them, which cost money and energy. Which is why the major players, such as NVIDIA, AMD, Intel, are still electronics. They did not shift to photonics yet. And the photonics designers are emerging startups, mainly American, such as Lightmatter, Ayar Labs, and Light Intelligence. But Scintille Photonics is a case in point of a European startup. The French startup based in Grenoble was just raised more than 50 million euros. So now you can understand why photonics can revolutionize AI computing, as light travels much faster. We can also do massive parallel data transmission with the Copters and the multiple wavelengths in one waveguide. And it also can be a solution for the GPU bottleneck problem, as the GPU with microelectronics don't have the computational power, and they have problem of computational power. In comparison, the issues in electronic chips is that every signal needs its own wire, and they have a lot of overheating and interference. And the signals can also degrade heavily over the wire.
Okay, so now let's see why this technology is vital for today, and especially in data centers. So actually, the main issue is not the computing power in data centers, but a bit more the GPU connectivity, because all the GPU needs to talk with each other in order to train AI model. And so all this information goes through copper cables. The problem of it is that it heats up, it consumes power, and it saturates really quickly. According to hyperscalers, most of the time, more or less 50% of the time, GPU are just waiting due to this latency, and this is important due to the copper cable they use in data centers. This is why we met Lightmatter. So Lightmatter is an American startup valued for $4.4 billion, and they raised $400 million in Series D series. And so the promise is to remove all the copper cable and to replace it by photonic interconnectivity, and so to gain in heat and consume less energy. So the promise, is in the long term to go 300 times faster than what we do now. And how will they do this? First, with the GPU utilization. So actually, it's 30 to 70% of the time all the GPU are working. And they would like to go to 80, 85, or 90% of the time to use simultaneously all the GPUs. And it will permit to train AI model 3 to 7 times faster than what we do today. So today is like few months for a big model. It could be a few weeks, for example. And also with the TCO cost. So by removing all the copper cables, you remove all the heat that the copper cables creates. And also you remove all the cost you use in order to cool down the heat that could have been created. So actually, in data centers, they're using the NVL72. This is a big fridge, 2 meters of height, 1.3 tons of weight, and 90 kilograms of copper cables on the back. It costs millions, and actually it doesn't resolve the problem of the bandwidth. So same thing, 50% of the time the GPU are working. And so Lightmatter would like to replace it by the Passage technology. So this is built in chips with several layers, and everything is happening here, so there is no cables. And you plug all the GPU and switches on the passage photonic technology. And so this is, for example, a quick overview. This is the NVL72, so it's huge, it consumes, and it's not so easy. And this is the size of the Lightmatter M1000. This is like a box of chocolate. It's really small, and this is the same usages. So it is planned that the compounded annual growth rate of the data AI market will grow by 29% for the next 4 years, and will reach 30 to 35% of market share for the next years. So this is where the money flows, and this is where investors are today. Another use case we can do with photonic technology is the Edge AI. So actually, you can run some models such as Llama 7B on your phone locally. But if you could try to run a model locally without any internet connection, cloud connection in your phone, with, I don't know, thousands of billion parameters, you would have enormous problems with the battery, the heat that would be created, because electrons consumes a lot. And here, with the photonic chips, you remove all of these problems, and actually you could run a model like this locally. And so a drone, for example, could be 100% autonomous with that kind of thing. So geopolitically, actually, the United States dominates all the market. They have pretty good players such as Intel, Nvidia, Broadcom, and some pretty good gems, just like Lightmatter or IR Labs we talked about. They invest a lot and push the innovation. For example, with the CHIPS Act, they raised $52 billion for this industry. The Europe, in that case, is a more paradoxical situation. We have pretty good players also, with STMicro or Quant in Germany. And we have pretty good laboratory research, such as the CEVA in France or the IMEC in Germany, in Belgium, I think. And we had a problem. This is the financial muscles that we're trying to solve with the European CHIPS Act. But to me, there is another issue that is the entrepreneurship field that we don't really have in Europe, and that they do in China or in the United States. And concerning the China, so yes, the ambition is to gain sovereignty in Europe with this. And the problem with China is that I don't think that we have to underestimate them, because they already showed by the past that they know how to produce and at a fair price and with a pretty good quality, with the 5G and a lot of batteries. And for them, it's not a game, actually. It's really a question of survival, because with the photonic technology, they do not have to use the EUV lithography technology, and they would like to bypass all the sanctions that America put on them with the 2 nanometers and the exports on the territories. So why and how invest on it? So to me, the question is not will it work, but who will win? The AI demand double more or less all the 3 months, and the photonic technology is the only way to answer to the wall we face. So the market targets 97 billion by 2034, and the barrier to entry are pretty huge in this market. With the physical, you have to make all these chips, and also there is issues with softwares. And those who master this tech will hold a de facto monopoly, which means that as soon as one actor has a functional solution, it will be complicated to do wafers. So if you want to play it safe, you have 2 actors that are implemented on this sector, Nvidia and Broadcom. Of course, do not just buy randomly. There is issues concerning the valorization of this company. Fundamentally, they are pretty good. They are making a lot of cash, but be careful with the valuation. Look at the price to free cash flow, PE ratio, PE forward before investing. The all-in bets, so you have Lightmatter and IR Labs. If you want, actually the risk is higher total, but the gains are asymmetric. So if you have 1 coin to put, you can choose between those companies if you want. And for me, the safest bet and the most interesting is the hyperscalers that are the high-end customers. and they are already working on their own solution they will develop. And actually, Google, you had a pretty good prices 1 year ago on Google with attractive valuation. Actually, it's a bit too high, but to me, the safest investment and the upside is limited, but will depend on the perspective and the long-term growth outlook of these two companies. Thank you.
Any question in the audience? So I've got questions. You mentioned Sentinel, right?
Yeah.
Okay. Where the technology is coming from?
One number.
Which organism?
I just know the name of the startup, but I don't know the name.
The technology is coming from, the patents are coming from. I guess in the audience. Wearables, microelectronics.
It's been called. I suppose so.
It's Syrup. It's Syrup and stuff. So CEA in the world. And they raised money from.
I think it was from Ocean Capital.
Isn't there an investment from NVIDIA?
There was a startup in the CEA that NVIDIA wanted to invest in for $500 million, but I think they refused in order to gain the independence. I don't know if this is the one you are talking about.
Yeah, I'm not sure, but I think I've heard that NVIDIA wanted to invest in.
Wanted, but I don't think that they could.
Okay. Anyway, that's maybe a good sign. You mentioned IMEC at the end of your talk as well. IMEC.
IMEC, yeah.
IMEC. You said it was in Germany?
In Belgium, I think.
Belgium. Yeah. Do you know where they're coming from?
Where they come from?
Yeah.
No, I do more or less what they do, but I don't know.
What do they do?
This is laboratory research, so they are working with ASML, and they put all the stuff, 350 million machines, and so in order to understand how the technology works, and so they implemented these machines in the IMEC.
Okay, so they have clean rooms, and basically they come from Philips. It's Philips behind the room. And you didn't mention that. Do you think SOI or SOI technology could be any use in optical?
SOI?
SOI, you never heard of it in your research?
Yes.
Okay. Some people think it could be interesting to use SOI for optical communications. So you have more options to invest in. So you at the end you invest in Microsoft, right?
So I prefer Google, but both are pretty good.
Okay. For photonic communications.
But actually, they're working on their own development of photonics. I think they have the budget in order to develop a pretty good solution. But actually, it's a bet. But they do a lot of cash from the other aspects. So actually, the risk is really limited because even if they do not succeed with the photonic solutions, you do not lose any money because they will continue to work on anything else.
So kind of safe investment.
Yeah.
Okay, thank you very much.
Thank you.
Just a remark, could you add sources, the URL under the picture you have? So that you can see. Satellites, right? So the floor is yours.
So welcome everybody to this presentation, which is going to be about satellites.
First of all, let's get started with a bit of space context about satellites. You need to know that satellites are classified with their weight. There are more or less 5 to 6 categories, ranging from CubeSat to what we call the legacy satellites, which are ranging from 400 to 5,000 kilograms, and you can get really small ones from 10 to 30. Another fact is that as of October 1st, 2025, there are approximately 13,026 satellites orbiting the Earth, which have the grand variety of purposes, ranging from the internet, the telecommunication, Earth observation, navigation, and also the scientific mission and more. A large share of the satellites, active satellites, are due to are in low, what we call the low Earth orbit, LEO, and which are mostly used for internet and telecom. This is what you can see with, for example, the Starlink and the Starlink from Jeff Bezos. I don't know really the name. And it also explains the rapid uptick in the total recent count of the satellite. There's more and more satellites every year, and those active satellites are not counting the fact that we have dead one in our orbit as well. So let's get a bit. Let's dive in what satellites are made of and what components they use. So satellites are made of several key parts. The first, we have the frame in the bus, which is the main structure that holds everything together. Then we got the solar array panel, which provides the energy for the satellites to operate. To communicate with Earth, they each got an antenna that transmits the collect data to Earth. And then we got the payload. The payload is specific to each satellite because it can serve different purposes. This one, for this example, is an optical sensor for Earth observation, or it can be also a radar for imaging, a space telescope for astronomy, a laser transmitter for high-speed communication. And we mentioned this one, that they've also got each thrusters, which help the satellites maintain its orbit and adjust its position. A good example is, for example, the Super Dove, which is a satellite about 6 kilograms and about the size of a shoebox, yet equipped with powerful instruments for Earth observation, and all that from a 550 kilometer orbit. All those components work together to make the mission successful. You can get other components on each satellite. For example, one we're going to zoom in is the Star Tracker. So a Star Tracker is a navigation instrument that identifies stars to determine the precise orientation of a satellite in orbit. It got several components that made it. The first one is the baffle. The baffle is a cylindrical shield mounted on the front of the tracker. It acts like a sunshade, blocking stray light from bright objects such as the moon, the sun, or even the Earth. And it prevents the light from entering the lens. It ensures also that only the light from the stars is in the direct field of view reaches the sensors, which maintaining high contrast. The second one is the optic parts made of, the optical system made of precision lenses, precise assembly of glass lenses, similar to a high-end camera, but designed for extreme durability. It collects the faint light from the distant stars and focuses it onto the detector. The lens must remain focused even under the extreme temperature that we can find in space. Then we got the detector, which is a photosensitive chip, or usually a CCD or a CMOS. A CCD is a charge coupled device. It converts the focused starlight into digital electric signals. Each star appears as a cluster of bright pixels and on a dark background. To analyze those data, we got the electronics, which is essentially made of processing units. It is the brain of the device, consisting of a circuit board with a processor and memory. Its function is to analyze the images from the detector, identifies the star pattern by comparing them with an internal catalog, which is called a star catalog, and calculate the spacecraft's precise orientation. So if you, to give you an overview of how it works, first is the baffle protect the lens, which focus starlight onto the detector. The detector takes pictures of the sky, and the electronic scan the image, find the bright spots, which are the stars, and measures the distance between them. And then it compares this pattern to a built-in map, which is called the star catalog, to figure out exactly where it is where it is pointing.
Now let's take a look at the life cycle of a satellite. So first, we have to know there are two different possibilities. The first one, which is like the legacy, it's when the governments, agencies want a satellite for different kinds of utilization. So for instance, we have ESA for the Europe, CNES for France, NASA. I think all of us know what is NASA. But also like defense agencies, we have the DRM, Direction du Renseignement Militaire in France. But we have also the National Reconnaissance Office for the US. So they are the guy making bad things, but yeah. And we have also, so those agencies will create like call of tenders to get satellites, and the companies, the private companies will work and they will win, then they will build the satellites. Or there are also the full commercial purpose, so that we see every day with the new space era. So it's basically company making satellites to make data and to sell it after, or this kind of use actually. So then they win the Call of Thunder, or they want to make a satellite, they build it, and then they will test it, because space is a very like complicated, difficult area to survive for a satellite, so they will try to make it like very sure to work. So yeah, they will test it. Then it will go on the rocket. For instance, here the Ariane 6.4, it's 4 because there are 4 boosters. They will be mounted on an adapter like this. So they will go to space, the launch, deployment, and at the end there will be the commissioning. So basically it's the ground antenna, like this one. They will like control the satellite to go to the right orbit. So it will be held by the launcher, of course, but then with the thruster, as we said, and they will use the data for the star tracker to see that they are in the right orbit. So when the satellite is in space, there is many possibilities, many utilization for it. So, of course, as we say, telecommunication, GPS or Galileo positioning systems, Earth observation. And the one that I would like to talk about is the future data center. That's the StarCloud is NVIDIA and Suncatcher is Google. They want to make like huge satellite in space, huge constellation of satellites in space to make like calculating for AI. And there will be like different kind of orbit, like GEO it's most of the time for broadcasting, and MEO it's middle. LEO it's what we say, it's telecommunication. And ESCAPE, it's really space exploration. Like, for instance, when we go to Mars or Venus or something like this. And the end of life of satellites, as the other group said, we have a lot of satellites in space now, and we have the possibility to reach what we say is the Kessler syndrome. So basically, it's at the end of the decade, we estimated that we will have 50,000 satellites in space. So there is a risk of collision between them, and if one satellite collides another, it will create debris, and those debris will, at the end, like collide with other satellites, and the risk is at the end we can't go like further than LEO. So it and also it will be the end of GPS and this kind of thing. So really the battlefield. So for that, we have thought about different things like orbit of debris. It's basically at the end of life we use the what will remain fuel to reach another orbit. A safe orbit actually. The other thing is to again use this remaining of fuel to go to Earth, and basically the spacecraft will disintegrate in the atmosphere. And the future is the EOL, so end of life OTV, orbital transfer vehicle. So this one is from ClearSpace, which is a European company. The idea is that those robotic arms will grab the satellites and maybe refueling it or just changing the orbits.
Okay, so now I'm going to talk about the key figures about the satellite. So we have 4 main points. So the number of HC in orbit. So early 2024, around 10,000 active satellites, including more than 9,000 in low Earth orbit, with roughly 2/3 belonging to SpaceX Starlink's constellation. The typical lifetime so for the GEO telecommunication satellites is between 15 to 20 years, and for the Helio constellation satellite is between 5 to 7 years, and in some cases it can be 10 years depending on the design and the mission. So for the cost range, a large GEO telecommunication is around 150 to 250 million for the satellite alone, with some programs reaching 400 to 500 million. The orbital launch cost is between 30 to 80 million, for medium class launchers, and around 67 million for Falcon 9, for example, and more than 100 million for certain heavy lift vehicles. And for the future of the SC, the European Space Agency project that the number of satellites in orbit could reach up to 100,000 by 2030, and if all planned mega constellations are deployed. And in a nutshell, these figures highlight the rapid expansion of satellite activity in orbit and underline how critical space infrastructure has become for global connectivity and data services. So now the satellite market size of the space economy. So the space economy market size, so we can see in this graph, that's projected for 2021 to 2034, and there will be a very big increase in the different market size, like the satellite industry, the non-satellite industry. So the global space economy is estimated around 596 billion in 2024, with an annual growth of around 7.4% over the past 5 years, and nearly 80% of this revenue comes from the commercial sector. And according to the ESA, the combined market for launch services and satellite manufacturing is 53 billion in 2023, of which around 80% corresponds to satellite manufacturing and 20% to launches. And the satellite services and their weight in the space industry. So for the commercial satellite industry, including telecommunication, broadcasting, Earth observation, navigation, data services, all that is accounted for 2,093 billion, representing 71% of the entire space sector. And in 2024, 259 launches placed 2,069 satellites into orbit, for a total deployed mass of 2,172 tons.
Now let's take a look at the big picture in 2024. So as you can see, here is the total revenue of the space economy. So half of it, to be the enable solution, it's all the data used from space. So basically like the Earth observation things that we, not the idea of selling the observation thing, but really using it. And the other half is really the space market. So as we say, really the manufacturing spacecraft, using it, etc. Other interesting thing is that we see that North America is the main actor, but Europe is close. And actually, we got the information a few weeks ago that they raised their budgets up to 30%. They were at 16 billions, and now they are at 22. So yeah, the interesting thing. Really, it's something to develop in Europe. And to finish, some French actors that are the competitor than the US one that we thought were interesting. So this one, it's the Legacy. Actually, they want to merge, to make one, like European giant in satellite space, this kind of thing. So it's Airbus, Thales, and Space, and the last one is like Telespazio, which is a BV between Leonardo and Thales. Interesting one is Eutelsat, because they're making the competitor of Starlink. It's not for commercial purpose like people for us, it's really for sovereignty reasons, but interesting to see what they will do. And Unseen Labs, it's a company that I like because they're making maritime surveillance based on RF technology. It's really interesting because with that we can see, like for instance, if China want to move an aircraft carrier, we can see it because with their software actually. So it's very interesting. Like the video on the LinkedIn is very interesting. And the other one, it's the one that we know. Again, Maybe Planet is interesting because as Rémi said, they're really making shoebox, that the company that revolutionized the spacecraft industry, because we this side and they have a lot of, I think it's 500 in orbit now, and they're the leader for Earth observation, sorry. And Amazon Leo, the competitor of Starlink for Amazon, and recently, at the beginning of this week, Blue Origin, they made an announcement that they will do their own mega constellation like Amazon Leo, but really this time it's only for Jeff Bezos, not only like the Amazon group. And last but not least, it's really very recent, so we didn't have time to include it in the presentation, but the exploration company which making a re-entry capsule, so basically something that go to space and go back to Earth, they just announced that they have a letter of agreement to buy a launcher company in Europe, which is interesting because at the beginning, SpaceX was doing the same thing. They just had like few fly to ISS, and they made their own launch today. And it's kind of the same way that they are leading, so it's interesting to see what they will become. So thank you everyone for listening.
Any question in the audience? So I've got one question. Can you you mentioned Leo and Geo quite a lot of time. Can you remember us the altitude in kilometers?
Yes.
And can you comment on that?
Okay.
Because Leo is supposed to be large, right?
No, it's low. It's low Earth orbit.
Large range.
What do you mean?
You said Leo is between 260 and 2000. So where is the main Leo altitude?
The main Leo altitude is 550 most of the time.
Okay.
And most of the time we use SSO, which is a kind of Leo that follow the sun because it's better for Earth observation.
Okay. And have you heard people changing in Leo altitudes, the altitude?
Yeah.
Which is?
The Starlink, they made it recently. Yeah.
And why did they make it?
Because the communication is better. They want to.
But why did they change the altitude of their Leo Starlink?
For many reasons actually, but yeah, the communication was better, and I don't know if you're talking about that, but recently they almost got satellite from Nepal, so that's why they're over the orbits, because there are other satellites in orbit. And
En français, vous avez entendu parler de Starlink? Ils ont changé l'altitude de leur satellite?
Oui, tout à fait. Mais
pourquoi?
Parce que la communication est meilleure avec le sol, ça va plus vite.
Il y a une raison. Vous n'avez pas prévu de changer l'altitude. Baisser leur altitude. Parce qu'ils ont eu un satellite qui a pété.
Ah oui, si, oui, tout à fait.
Il y a un satellite qui a explosé. Et donc en fait, si j'ai un satellite dans une constellation qui explose, j'ai des débris. Donc si mon satellite d'après il se prend les débris dans la tronche, voilà. Donc en fait, ils ont changé leur altitude. Et le problème, c'est que L'autre exposé commence à s'installer, s'il vous plaît, mais on va continuer la discussion. L'exposé suivant, s'il vous plaît, s'installe. Donc, la discussion, c'est personne n'est responsable de. Donc, monsieur Metz qui fait tester un satellite, il faut une altitude Léo, il se casse, il paye rien.
Le problème, c'est qu'en ce moment, il n'y a pas beaucoup d'agences qui gèrent ça. C'est
Non,
nouveau.
c'est pas le problème. Normalement, il
Il
ne
veut pas.
Je pense qu'il faut qu'il paye. Non, il n'y en a pas des masses. Donc en fait, là en ce moment, il y a une course à choper les altitudes en Léo. Vous avez compris là. Donc les Américains, ils ont Starlink qui met des milliers de satellites. Plus de Amazon qui met des milliers de satellites.
Les
Les
Chinois,
Chinois, ils sont en train d'en mettre. Et nous, il faut vite qu'on prenne les altitudes. Vous voyez ce que je veux dire? Et surtout, je pense qu'il y aura un problème. Parce qu'il y a eu un autre incident, je ne sais pas si vous avez vu en Léo. Il y a Starlink qui est passé à côté d'un.
Oui, c'est ce que je te disais, à côté d'un satellite népalais qui s'est joué à quelques kilomètres, 1 ou 2 kilomètres.
Ils avaient dit chinois au début. C'était népalais, c'est ça?
Non, mes souvenirs, il
Et en fait, au début, Trump, il a dit chinois.
Mais il me semble qu'il y a eu
Par
deux.
de dire,
Ouais, bah, ça
c'est
s'appelle
leur faute.
Pas la patate chaude.
Donc, en gros, je pense qu'il va y avoir une géopolitique des orbites Léo qui va être très.
En fait, le souci, c'est qu'il n'y a pas vraiment de document légal. Le dernier en date, c'est le traité de l'espace qui date de 1967. Et donc, c'est pas.
Mais là,
Pas du tout
on n'avait pas prévu. En ce moment, donc ça va. On est en train d'avoir une exponentielle du nombre de satellites en l'air. Et le problème, c'est que l'exponentielle, après tout, ça ne marche pas. Donc, allez, vous avez dit le dernier point, c'était les data centers.
Ouais.
Vous y croyez?
Ça va pas être facile en tout cas.
Déjà, le bruit qu'il y a, machin, truc. Un data center, déjà à terre, quand ça marche, on a du coup de bol. Mais alors, dans l'espace.
Là, c'est beaucoup de contraintes au niveau de la
S'il
dissipation de la
y a
chaleur.
des débris qui traînent, qui font le truc, comme ils vont avoir. Les data centers, quel est leur problème maintenant? Le vrai problème des data centers dans l'espace.
Il y en a beaucoup, mais la dissipation de la chaleur, mais aussi la résistance des composants.
Ouais.
Et puis aussi l'énergie, il va falloir des grands panneaux solaires pour les.
Et donc?
Ah ben, ça prend de la place et du coup ça demande.
Non, mais si j'ai des très grands panneaux solaires et j'ai plein de débris,
Oui, c'est
bien sûr qu'il va s'en choper. Vous voyez ce que je veux dire? Je veux mettre des data centers, j'ai besoin de beaucoup d'énergie, je fais des énormes panneaux solaires, je sais pas si vous voyez les photos de panneaux solaires qu'ils ont vus, c'était des trucs de kilomètres de je sais pas quoi. Mais dans aucun monde, il y a le truc se prend pas un débris. Il y a forcément une vis, un boulon de l'ISS qui va flasher. Et quand je perds un satellite, je pleure parce que un satellite ça vaut plusieurs millions. Et quand je perds un data center, alors c'est peut-être bon pour nous qui auront à dire, parce qu'ils vont en vendre. C'est-à-dire que je ne change pas la carte dans le data center, je change le data center. Ça me choque pas, c'est pas grave. Moi, ça me choque un peu. Voilà, merci beaucoup. J'espère que. Donc là, on fait la pause déj, c'est ça? Comme vous voulez, hein, ça on est au déj pour à quelle heure? 13h30, monsieur. 13h30. Vous avez l'ordre de passage après? Avant de partir, si vous avez des idées pour votre copain là qui se
Non mais vas-y, je fais la mets en promo de partie, peut-être que ça peut être mieux. Et en fait, c'est cohérent parce que genre, elle parle des applications. C'est ça, mais en gros, elle parle des en disant.
Parce que donc, tu vas faire un peu avant ton vidéo, et voilà, quoi. Tu veux pas, genre, tu dis juste que.
Mais du coup, non, c'est pas mal comme ça, tu juste tu me dis un truc. C'est pas bon, genre, si je la fais après l'application, genre, en gros, les applications, c'est pas juste théorique, il y a aussi des... Bah,
tout à l'heure.